So this is motion in one dimension, and this is the first part of it. And basically, we're going to start talking about things like displacement versus displacement, velocity, and acceleration. And we're going to compare that with distance, distance traveled, speed, and I think called pickup. Does your car have a lot of pickup? You know, can it change speed easily? We tend to spend most of our scientific time worrying about this bit as opposed to this bit. Although we've got to know both, but we're gonna use these terms an awful lot over the next 10 weeks or so. We might also look at how things changed on an instant. So we'll talk about instantaneous velocity and acceleration. We're going to ask ourselves a conceptual thing. You might have done it already about speeding up or slowing down. And then for this section, we're going to talk about graphs of motion. So average displacement versus distance traveled. When I was a student, I was a bit lax. So I would just glance at things and not sweat the details. And I'd go, oh yeah, displacement, it's like the difference between the two. And so sometimes I get the answer wrong because on that day I chose to use the initial minus the final. It's always your displacement, and that is one symbol. It's not a delta multiplying an x. It's a name. It's called delta x. There's only 26 letters in the alphabet, and we ran out of those a long time ago. So we have Greek symbols with our alphabet. We'll have a whole bunch of things. But that is a thing. It's called displacement. If you like, you can call it change of address, but you've got to be careful because it means specifically the final address minus the initial address. Okay. Displacement of an object is a vector. That means it's got a magnitude and a direction. The distance traveled is a scalar. It only has a magnitude. We don't care which direction. You can go around corners, whatever. It is the sum of all the motion without regard to direction traveled. So here's a typical example. An object starts at +3. So this is an exercise where I tell you about a journey. And my language has to be, well, you have to be able to interpret it. There's only so many things I can do if you think about it. I can tell you your address. I can tell you how far you are to the left or right of an address. 3 meters to the left of the origin, 4 meters to the right of the origin. The origin's an address. I can tell you you move to the right, you move to the left. I can tell you how far. I can tell you you go to a new address. I suppose I could tell you you go with a certain speed in a certain direction for a certain time. But there's only a few things I can do. So if you think about all the scenarios, you can make sure you got it covered. So let's look at this example. An object starts at +3 meters. So let's put a 0 down, and then I'm going to put a +3 here. It moves 7 meters to the right. Oh, okay. So now I've gone 7 meters to the right, and I'm at +10. Why? Because 7 and 3 makes 10. It moves to a point located at -12. Oh, we go all the way back here, and I'm at -12. So there's my start, and there's my end. So I have a system to this. I use a number line. I put my addresses below the number line. I show my motion with arrows. I'm careful to show all the little bits because especially we're going to get to the stage where I could ask you about any of this journey. And later on, when we're dealing with times, I'll actually regard this as a little clock. And I'll actually write in not S and E, but I'll put in 0 seconds, 5 seconds, 12 seconds, 15 seconds. So I have a methodology behind this. And then what's the question asked? Let's do distance traveled first of all. Distance traveled is actually a hard one. Distance traveled, it's the distance traveled. Well, let's have a look. That was 7 meters. And then we had another 10 meters, so that's 7. and then I add another 10 meters to get back to the 0, and then I add another 12 to get to minus 12. So that's going to equal 29 meters. There's no real equation for that. It's like you've got to intuit it. But on this side, my displacement is equal my final position minus my initial position, which equals, and now I look at my diagram, and I go, my final position is minus 12. And I subtract them from my initial position. My initial position was plus 3. So my delta x is equal to minus 12 minus, I shouldn't have put my brackets, but minus 3, which equals minus 15 meters. There's my answer. Should have put that answer in a box as well. And I can actually see that if I come down here. Let me show you that. That is, oh great, same color after all that. That is that. On my diagram, my displacement is that. It's from where you start directly to where you end. And if you look at that, that is minus because it's pointing in a negative direction, and it's 15 units long because it's 3 there and 12 there. So you can actually get it from the diagram as well as getting it from the equations. So distance traveled, displacement. I'm careful about signs and operators. That negative sign there is part of my address. That negative sign there is an operator. It's a mathematical thing. They interact with each other and you know how they interact, but I want to make sure that I don't get my operators confused with my direction signs. So I tend to put things in brackets, parentheses, a lot more than I used to do. So my advice is you do that. If it's a thing, put it in parentheses. If you've got to add or subtract it, it goes between the parentheses. You'll make fewer slips on that. Questions on that? Cool. Average velocity is a vector. It has a magnitude and a direction. Average speed is a scalar. It only has a magnitude. The speed is the distance traveled divided by the time taken. And the average velocity, it's got a little bar on top of it. It's not like balanced, it's average. The average velocity is my displacement over my change in time, which equals my final position minus my initial position over my final time minus my initial time. So let's do it. We say an object starts at +9. It moves 6 meters to the right in 4 seconds. So it's going to go to +15. And that took 4 seconds. So I've got to bring a clock in. I wasn't given a starting time, but I'm going to call the starting time 0. And then I'm going to call this 4 seconds. I could have called the starting time 5 seconds, in which case I'd now be at 9 seconds. It doesn't have to start at 0. And sometimes I'll tell you an object starts at +9 meters at t equals 3 seconds. And I'm trying to find out, do you know to take the final time from the initial time, or are you always going to take things away from 0? So be careful about that. And then the object is then stationary for 5 seconds. So let's just do that. It didn't move, so don't move it. But we've got a different clock. And then the object then moves 3 meters to the left in the next 2 seconds. So 3 meters to the left. That means I'm at +12. And it took 2 seconds, so that's going to be 11. Now, I didn't use most of this page, and I don't care about that. You know, I did a decent diagram. It's clear to me. I'm not trying to save wood and all that kind of stuff. It's like, I just want a decent diagram. My average speed, my speed is equal to my distance traveled over my time taken, which equals, my distance traveled equals, well, 9 to 15 is 6. and then 15 to 12 is 3, over my time taken. My time taken was from 0 all the way to 11. So that would be 9 over 11, which equals, did I bring my calculator? Yes! Yes, I'm a physics person. I bring my calculator all the time. Having said that, I'll forget it next time. But so this is 0.8181. And I like it to give me a couple of decimal places, so that would be 0.82. It would be meters per second. Put it in a box. Average velocity. Average velocity equals my displacement over my time taken, which equals my x final minus my x initial over my t final minus my t initial. I look at my diagram and I go, well, my final position is plus 12. And I'm going to subtract from that. My initial position was plus 9 over, and my final time was 11 minus my initial time, which was 0. So my average velocity equals 12 minus 9 is going to be plus 3 over 11, which equals 3 divided by 11 equals 0.27 meters per second, and it's a vector. So I'm trying to get myself in the habit of, it's a positive. I tend to put signs down for vectors. I don't bother about signs for scalars because they're always positive. And in a way that tells me, oh, that's a scale. I think that's a scalar. I don't have a sign. Oh, I think this is a vector because I put a sign down. Cool. Average acceleration. So, average acceleration is a vector. It has a magnitude and a direction. Average pickup is a scalar. It only has magnitude. An object has a velocity of plus 5 meters per second at t equals 7 seconds. I have no idea where I am, so that's no big deal. I'm going to have my little clock. I'm going to have my clock saying 7 seconds. I'm going to have a little arrow on here saying plus 5 meters per second. The object has a velocity of minus 17. Oh my word, minus 17. So I'm going to put it like that. Minus 17 meters per second. And this is at plus 25. What is this average acceleration during the time taken? The pickup would equal my change in speed over my change in time, which equals, well, that's a speed of 17, and that's a speed of 5, so that's 17 minus 5 over, and that's 25 minus 7, 25 minus 7. So that would be 12 over 25, that is. 12 over 18, which equals 0.66 meters per second per second. I learned it as meters per second per second. It's the change in velocity in a given time. These days they say meters per second squared, which is mathematically nicer, but I think obscures the meaning to some extent. Meters per second, every second tells you it's a velocity divided by time. If I took at my average velocity, so my average acceleration equals my change in velocity over my change in time, which equals my v final minus my v initial over t final minus t initial, which equals, now I'm looking at my diagram, my final velocity is minus 17, minus my initial velocity is plus 5, over my final time is 25, minus my initial time is 7. So this is going to equal 17 minus 5 is going to be minus 22 over 18, which equals minus, oh dear me, wrong thing, minus 22 divided by 18 equals 1.22 meters per second every second. Very different answers. Any questions on that? People ask me, they say, why do you write down all that VF minus VI? And I say, it's constant training. It's like turning around to, you know, Mr. Universe and saying, why do you go to the gym? Because I want to stay fit. Well, by writing down that equation every time I do this problem, I reinforce it so that on test day, I'll know it. I'm not going to learn that the night before the test and then on the test second guess myself because I can't remember if it's final minus initial or initial minus final. You'll decide your test grade this week. If you're doing homework already, it bodes well. If you're leaving the homework until the 2 days before the test, you will not do as well as you would do if you started now. And if from now on you sweat the details and you write the stuff down, it will just get stronger and stronger and stronger. If you just write down numbers on a page, all you're practicing is writing down numbers on a page. And you already know how to do that. So I really would advise you, just copy this. I'm a successful physics teacher, maybe not successful in life, you know, but I can do this. And it took me 20 years of teaching to get to this stage, never mind the time in industry. 20 years just trying to teach this stuff to get to this stage. And this is the final result of all that. That didn't work, let's change something. This is what I came out with. So why don't you just cheat and copy from me? Okay? It's like, I'm not trying to make you into physics angels. It's not like this is going to make you a better person. It means you're going to get a better grade. Okay? So take my advice and do it. Let's start now. Can you do that problem for me, please? I'm going to put a timer on. I'm going to pause my computer so that you don't need to see this thing like paint drying. Okay, so we're back. So let's stop the clock and see what people are saying. So mainly A, a little scattering of other things, but mainly A. So let's just see where that comes from. So we say, okay, let's use our standard methodology. Let's find a pen. Where do I do that? Yeah, there's my pen. Yep. So we're going to have our number line, and it says at t equals 3 seconds, the car is at minus 16 meters. So minus 16, and my clock says 3. And then at t equals 9 seconds, I'm at plus 6. So here's plus 6, and my clock is saying 9 seconds. And then at t equals 12 seconds, I'm at minus 8. So minus 8. And this is saying, my clock is saying 12 seconds. So I went like that, and then went like that. 3, 9, 12, 3, 9, 12, and then 16, 6 plus 6, and minus 8, yes. And it says, I want to find, on one hand, it wants to find the displacement. Well, the displacement is equal to my final position minus my initial position. So my displacement is equal to, and I'm looking here, and my final position is minus 8. Minus my initial position is minus 16. And so my delta x is equal to minus 8 plus 16. So my delta x is equal to plus 8 meters. And then on my distance traveled, I go, well, let's have a look. My distance traveled, is it the sum of all these distances? So that is basically 16 to get me to the 0, and then another 6 to get me to that point, and another 6 to get me back to the 0, and another 8 to get me back there. So my distance travelled would equal 16 plus 12 is going to be equal to 28, plus another 8 is 36 metres. So that's what I'm thinking. I'm thinking plus 8 metres and 36 metres. Oh, plus 8 and 36 is A. Yep. Cool. So I used the same methodology, didn't I? I did a diagram, and then I wrote down my principles, my equations, and then I interrogated my diagram to get my numbers. The math is not what it's all about. It's all about the diagram and the actual equations that you use, really, isn't it? So, good. Do that one for me, please. So we're back. Let's stop this, and then let's look at our graph. Mainly people saying C. Let's have a look and see where that comes from. So again, we draw ourselves a nice diagram, and we say at t equals 5 seconds, the car is at minus 16. So here's my 0. Here's minus 16, and this is at 5 seconds. And then at t equals 9 seconds, it's located 6 meters to the right of the starting point. So that's going to be minus 10, and that's going to be 9 seconds. 6 meters to the right of the starting point. So it was at minus 16, now it's at minus 10. And then it says after another 2 seconds, it is at minus 12. So here's minus 12. And that is going to be another 2 seconds, we'll make that 11. So we went like that, and then we went like that. So what do I want to find out? It says, what is the average velocity? My average velocity is equal to my displacement divided by my time interval, or my duration, if you like, which is my final position minus my initial position over my final time minus my initial time. And now I'm looking at my diagram, and I'm saying, what is my final position? I ended up here, so it's minus 12 minus, what's my initial? I started off here. That's going to be minus 16. And then what is my final time? Well, I had 5 went to 9, but then it said, and another 2 seconds, so 9 went to 11, so that would be 11 minus, what was my starting point? Oh, I started off at when the clock said 5 seconds. That's going to be minus 12 minus 16 is minus 12 plus 16, which is plus 4 over 11 minus 5 is plus 6, which is plus 0.66 meters per second. Cool. So there it is. So look at if you did not get it right, then, or even if you got it right, but look at, certainly if you didn't get it right, did you have a diagram? If you didn't have a diagram, I think you're kind of shooting yourself in the foot. That's the skill you got to work on. If you had a diagram, was it correct? And then if you had a correct diagram, then did you write down the equation? Again, my sense is if you don't write down the equation, you just put in numbers on a page and you'll make slips. If you had the right equation, then did you put the numbers in the right order? And then if you had the numbers in the right order, did you get the right number? If you made a mistake on that bit, it's math. If you made a mistake on that bit, then it's basically interpretation of what those letters mean. If you got that bit wrong, it's not knowing your equation. If you got that bit wrong, it's your visualization. There's like 5 skills in this question, and you might have 4 of them right, and 1 of them you might have messed up on. And if you're consistently messing up on 1 of them, that's the weakness that you've got to work on. It's not that, oh, I got it wrong, better luck next time. It's that doing that. I never used to do postmortems after a test because it was depressing. That was a mistake. But you should do postmortems as you're doing homework. About when I was in the 11th grade, digging a hole for myself in math because it wasn't going well. I could not get the answer in the back of the chapter on my first attempt. And I would fiddle with the question until I got the answer at the back. And I had, in the end of the year, I had a correct solution to every problem in the book, but couldn't do any of them on a test because I could never get the answer right the first time, and the test did not have the answer in the back. So I'd learned really nothing, and I knew in my gut that I was in trouble. But as I say, I think I told you, I had these two teachers who just kept passing us. You know, I wasn't doing great, but I was passing comfortably. And yet, I had this feeling that this wasn't right. It never occurred to me to say, man, I can't get these right the first time, and why can I not get these right the first time? So try and be very analytical with yourself, especially before the test. On test day, I think you've got to go out and have a cup of coffee and just relax and just, you know, pat yourself on the back for a job well done, you know, and you've got to be kind to yourself on test day if it don't go well. But before test day, you've got to be kind of hard on yourself, and maybe after test day, you've got to be hard on yourself. But be very analytical about why things are not going the way you want them to go. It's all logic. It's just you're not familiar with it. You do far more complicated things than this every day, but you've learned how to do them and you practice them. So you got to keep on. Let me do this one. Car starts from rest. So here's my car, and it starts from rest. So V is equal to 0 meters per second. After 4 seconds, it has a velocity of minus 12. So I'm going to put 4 in my clock, and now it's got minus 12 meters per second. What is this average acceleration during this period? Average acceleration is equal to my change in velocity over my change in time, which equals my v final minus v initial over t final minus t initial. If that was 4 and it was after 4 seconds, that's 0. So then I say, okay, my v final is minus 10 minus my v initial. I started off at 0. I'm sorry? Oh, thank you ever so much. Minus 12. Yeah. Oh, look. So now, there's an interesting point. Look. I made the mistake there. Okay? But I wrote it down. And then I transcribed it there. But I wrote it down. And if I'd continued and got the wrong answer, it would be wrong. Wouldn't be perfect. But it wouldn't be as bad as if I'd done something crazy. By writing that down, there's a chance I will get some credit for that. If I just have the final answer, I get nothing for it. And yet it was just a transcription error at the front end. You can't just ignore transcription errors all the time. But a transcription error is not as bad as not knowing the equation. You know, so you've got to help me to kind of help you. That's 4 minus 0. So that's going to be minus 12 over 4. My average acceleration equals minus 3 meters per second every second. Did I get that right? Cool. Okay. Let's talk about instantaneous velocity and instantaneous acceleration. So, average is take the final and take the initial and assume it changed gradually. That's what average is all about. Sometimes you know it doesn't go like that. Sometimes you know you speed it up as fast as you could, but as you reach your maximum speed, you got quicker, slower and slower and slower. And you want to know, well, where am I at a particular instant? What am I doing at a particular instant? So this is where this comes in. Graphically, if I'm plotting position or address or coordinate versus time, I'm starting off at a certain value and I'm moving. As time passes, you can see that I move at a slower pace further away. I'm taking smaller and smaller steps in position for the same amount of time. My instantaneous velocity is the change in position over my change in time at that instant. So you basically find it by doing the tangent. You take this little bit of slope and you push it out as a tangent, and then for that little tangent you find the rise over the run, my delta x over delta t. That's graphically. If I wanted to do this thing in terms of calculus, what I'd do is I'd turn around and I'd say, okay, yeah, I'm going to imagine 2 points on this line, and I have my rise over my run, and I imagine sliding one of these points towards the point of interest, and in the limit, as my little delta t goes to 0, I say, what is my slope? So we imagine this line, this arc, this chord, if you like, get in. Until eventually it's a tangent. We're kind of doing the same thing. One's mathematically, one's graphically. And we say, well, that equals dx by dt. And I know how to do dx by dt because I've done calculus 1, so I know how to do that. Instantaneous acceleration, I'm just dealing with a graph of velocity versus time. It's the same argument. I can basically get the tangent to that graph and get my change in velocity over my change in time. Or I can say, well, in the limit, as my time interval goes to 0, it's my change in velocity over change in time, which is dv by dt. And if I remember, my a was equal to dv by dt, which equaled d2x by dt squared. Yeah? You've done this. I'm sure you've done that in Calc 1. If not, if it's been a while, sometimes people they have a big gap between Calc 1 and this. If it's been a while, then just review it. What is the instantaneous velocity of a particle whose position is defined by? Now, you know, this is a little bit of me teaching. I wouldn't do this if I was doing this on a test. If I was doing this on a test, I'd do, oh yeah, it's something like that. And I'd say, oh, it's between, at time, what is instantaneous velocity at times t equals 3 seconds? I'd draw something like that. But, you know, I want this to be a little bit better, so I'm going to cheat a little bit. I'm going to say, well, let t equals 0, so that's going to be minus 7. And when t equals 1, that's going to be 2 plus 4 is 6, minus 7 is minus 1. And then when t equals 2, that's going to be 2 2s are 4, 2 4s are 8. 8 plus 8 is 16. 16 minus 7 is going to be 9, so plus 9. So my slope actually looks like that. Now, I would not do that on a test. I just want to kind of give you a feel. Oh, and of course I did 3 seconds. So I'm interested in a point that's way up here somewhere. So I'm looking for a slope like that. Yeah, this is my position versus my time. And my velocity is my slope. What do I say mathematically? I say v equals dx by dt, which equals d by dt of, well, what is my x function? It's 2t squared plus 4t minus 7. So v is equal to, and what is it? Multiply the power by the coefficient and reduce the power by 1. So that's going to be 4t plus 4. And I want to know what this is at t equals 3. So v at t equals 3 is going to equal 4 times 3 plus 4, which equals 12 plus 4. V at times t equals 3 is equal to plus 16 meters per second. Is that right? Did I do that right? Good. Okay. So notice I'd have a little, even when I'm doing it, I might not have the right graph, but I would have a little graph just to say, oh yeah, this is what I'm doing. I'd have my slope on there. I'd write this out. There's my principle. I've plugged in my value. I'm doing my math so that even if I mess up on the end, you know, I can, first of all, when I'm checking it, I can eyeball this and check it. Did I add those two up right? Oh, yes, I did. Did I do this right? Oh, yes, I did. The math is right. Now, is the math on the right problem? I can check it. If you only write down a few things, you can't check it. What is the instantaneous acceleration? So I'd say, okay, now I have a position versus time graph, and I have a point of interest. So I say A is equal to dv by dt, which equals d2x by dt squared. So I want, let's do it in steps. I'm going to say v equals dx by dt, which equals d by dt of 3t squared minus 2t plus 6. So v is equal to 6t minus 2. And then we say, well, a is equal to dv by dt, which equals d by dt of 6v minus 2. So a is going to equal 6 meters per second squared. And it doesn't matter what my time is. It comes out to be a constant. Agreed? Agreed? Yep. Hopefully it's there. And in retrospect, it'd be nice if it had a letter in front of it to say it was A. And also it'd be nice if it had a sign in front of it saying it's positive. So that's right? Yeah, cool. We're going to do this last little bit, then we'll take a few minute break and we'll come back and push on. So speeding up and slowing down. Speeding up and slowing down. Most people, when they begin, make a mistake. They get the idea that positive addresses are to the right and negative addresses are to the left. They get the idea that going in a positive direction is a positive velocity and going in a negative direction is a negative velocity. And so they intuit from there that a positive acceleration is speeding up and a negative acceleration is slowing down. And that is absolutely not true. And I can prove that to you pretty straightforwardly. Let's say I throw a ball in the air. So let's say I throw it up. So at time t and v. Let's say that time t equals 0, I throw it upwards with a speed of 30 meters per second. So it's going upwards at 30 meters per second. I know my acceleration due to gravity is equal to minus 10 meters per second squared. We've done that, yeah? You did that in fundamentals of physics, yeah? Okay, so then that means that after 1 second, what do? I simply, this is the change in velocity per second. So after 1 second, this is my change in velocity. I add on my acceleration number. So plus 20, plus 30 becomes plus 20. And after 2 seconds, it becomes plus 10. And after 3 seconds, it becomes 0. And after 4 seconds, I still add on minus 10. So minus 10. After 5 seconds, it's minus 20. After 6 seconds, it's minus 30. Notice, my acceleration is always negative. And yes, initially, I am slowing down. The ball goes up and it slows down. Isn't that what we decided? But watch. Once I stop, I still have a negative acceleration, but now I'm speeding up. I'm speeding up in a negative direction, but I'm speeding up. So the sign on the acceleration by itself does not tell you if you're speeding up or slowing down. It's the comparison with the velocity. So if I have a positive velocity and a positive acceleration, I speed up. If I have a negative velocity and a negative acceleration, I speed up. This is speeding up going in a positive direction. This is speeding up going in a negative direction. But I'm speeding up. If I have a positive velocity and a negative acceleration, I am slowing down. I'm going in a positive direction, but I'm slowing down. And if I have a negative velocity and a positive acceleration, I am slowing down. I'm going in a negative direction, but I'm slowing down. So you take the sign of the velocity is always the direction you're traveling in. But the acceleration sign does not tell you if you're speeding up or slowing down. It simply tells you in comparison. Okay? And that's what this says. When the direction of acceleration is in the same direction as the velocity of the body is speeding up, and when the direction of acceleration is in the direction opposite to the direction of velocity, you're slowing down. Here's a question. At t equals 5 seconds, an object has a velocity of plus 2 meters per second and an acceleration. This is where, frankly, it's a bit of a pain for me. But for you, if you've got one of those pens especially that clicks, you can never get your velocity and your acceleration confused because you have them different colors. So minus 8 meters per second squared. Characterize its direction of motion and rate of progress. Rate of progress means acceleration, speeding up or slowing down. So direction of travel, positive direction of travel, and slowing down. My writing's, I'm rushing, so my writing's horrible, I'm sorry. Slowing down. So can you do that one for me? And then we'll take a break. Okay, so let's stop that and have a quick look. Most people are saying B. And let's have a look, little look. T equals 4 seconds, so there's my 4 seconds. Velocity is minus 12 meters per second. And acceleration is minus 4 meters per second squared. So I am speeding up, but I'm going in a negative direction. So speeding up going in a negative direction should be B. And I think that's what most people said. Yeah, it's B. Okay, let's take a break. Let's stop this. So welcome back. So the next thing is going to be motion graphs. So this is not the same journey. I'm plotting position or address or what have you versus time. I'm plotting velocity versus time. I'm plotting acceleration versus time. And I'm showing you a linear trace just because it's easy to talk about. When you get a trace like this, there's two questions you usually ask yourself. One is, what does the slope mean? And the other one is, what does the area under the graph mean? Under the graph meaning to the 0 axis, not to the bottom of the page. Because now we have negatives. The bottom of the page can be whatever I choose it to be, minus 25, minus 30. It's to the axis. It's to the 0 axis. And you can figure out what it means actually by looking at the actual units or the dimensions. If this is a coordinate versus time, that's meters, and so this is in meters, and that's in seconds. So the slope would be the rise over the run. Well, the rise is measured in meters, and you divide it by the run, which is measured in seconds. Oh, that's got units of velocity. So the slope of a position versus time graph is velocity. The area under the graph, well, that's going to be meters times seconds, meters seconds. And it exists, but there's no clear physical interpretation of it. We say it's got no clear meaning. Not so useful to us. If I go with a velocity versus time graph, this is not the same journey. If I have the graph on the left, I cannot get the graph in the middle for the same journey. It doesn't look like that. So I'm just showing another graph. But if I have a velocity versus time graph, I have meters per second for my rise, and I have per second for my run. Well, that's acceleration. So the slope of a velocity versus time graph is acceleration. Whereas if I do the area under the graph, it's meters per second times seconds, which is meters. And meters is the measure of displacement. So, okay, the area under the graph gives me displacement for a velocity versus time graph. And if I look at an acceleration versus time graph, for the slope I get meters per second divided by seconds. Oh man. Which is actually meters per second cubed. which is actually, anybody know what that's called? It's called jerk. It's the rate of change of acceleration. And because acceleration is connected to excess forces, it's the rate of change of your excess force. So when you hit something to make the door handle open, rather than pushing it slowly, when you hit it, you're jerking it. And it has physical significance. How quickly you change that acceleration is important. And so, because, and physicists don't talk about it much, no clear meaning. That's wrong. It's actually jerk. And the area under the graph is going to be meters per second, times seconds, which equals meters per second, which is velocity. Cool. So what do we do with this? Well, we do graphs like this, where we take a journey. Now, realistically, if I have a time span of only 7 seconds, and I have these velocities, these positions, or these velocities, I'm working on a particle. If I did this with a car, I would get rounded edges. Having a sharp change like that is really incredibly hard for anything with mass. But if I had hours rather than seconds, you could get a graph like this. And what we do is we try to interpret these graphs. And the way we do that is we ask ourselves questions about it. The problem is the same problem we have with all graphs, which is we tend to look at the shape of the graph and not the axes. So if I have it in my mind that I'm dealing with velocities and times, I will tend to look at whatever graph I see next as a velocity time graph. And if I have it in my head that I'm dealing with acceleration and times, the next graph I look at, I'll tend to interpret as an acceleration versus time graph. And often I'll see that if the question preceding this is of a different flavor than this is, people will interpret it in the incorrect way because they're still in their mind thinking about the old system. So with graphs, my advice, especially at the beginning, is as a habit, you put circles around what the axes are and you say it to yourself, not out loud in class, please, but you say it to yourself. Oh, this is a such and such. Because it's a shame to know how to do it and get the whole thing wrong just because you think it's the wrong type of graph. There's another kind of subtle way, which is whenever I check my work, I go from the last question to the first question. So first of all, test-taking technique. When I get a test, I look at the whole test. I check all the ones that I think are easy. I put X's by all the ones I think are very hard. I do all the easy ones first. I then do the ones that don't have anything next to them. I'll then do the ones I think are very hard. I don't care about the order. The order was given to me by the examiner. They can do it in whatever order they like. I'm going to do it the easy ones first, then the next group, and then the hard ones. I remember at USF, I had a student who got 16 out of 16. 16 perfect answers, except the test had 25 questions. And I said to the student, look, what happened here? Well, I ran out of time. Why did you run out of time? Because I couldn't do question 17. Could you do question 18? Oh, yeah. 19? Oh, yeah. 20? Oh, 20 is easy. He should have got one question wrong. But because he determined he was going to do them in order, he got all the rest wrong. Why would you do that? So, do the questions in the order. If you're going to burn time at the end, have it on the question you can't do, not the question you can do. Second thing, whenever you check your work, most people finish early. They've got plenty of time to spare. They can check their work. Go in the wrong order. Don't do it the same way. Because if you've got velocity and time in your mind and you have a graphical question, and it's really a displacement versus, or a position versus time graph, and you made that mistake, if you're coming from the other direction, the chances are you won't have velocity and time in your mind. And you'll go, oh, yeah, I misinterpreted that. So just, you know, just be careful. I don't want you. This course is hard enough. I don't want you giving points up for easy stuff. You know, if you lose a point, I want it to be that I genuinely didn't know that. Not that, oh man, I could have got that. So just try and be a bit careful with it. So watch out for your axes. And then there's different rules for these different graphs. That's the problem. So we know that in this graph, that slope is an acceleration. It is a velocity. It's a straight line, so I know it's a constant velocity. It's a positive straight line, so I know it's a positive velocity. I know that object is traveling in a positive direction. I can even tell you that it's going to be plus 20 over 1. It's plus 20 meters per second is that velocity. I can tell you that this object is now stationary. It's got 0 velocity. It's not moving. I can tell you it's got a certain positive velocity. It's not as big a positive velocity as it was initially. Now for this next second, it's traveling at 10 meters per second. I can tell you now that it's traveling at a steady negative velocity. And the negative velocity is minus 10, 20, 30, 40, 50, 60, minus 60 over 2, minus 30 meters per second. I can tell you it's stationary again there. I can tell you it's got a positive velocity then. I can tell you that it's going fastest between 3 seconds and 5 seconds. It's got the biggest negative. It doesn't matter. It's going fastest between those two. I can tell you it's stationary for the first time, comes to a halt for the first time at 1 second. I can tell you it passes the starting point at 4 seconds. I can tell you it changes. When does it change direction for the first time? What time does it change direction for the first time? Stop going positive, start going negative. It is 3, isn't it? Positive velocity, negative velocity. It's not 4. Okay? That's when it passes its starting point. Come over here. Well, hold on. This is velocity versus time. I can tell you there's a constant acceleration for the first 2 seconds, and I can tell you that constant acceleration is plus 2.5 meters per second squared, because it's plus 5 in 2 seconds. I can tell you then go to, again, a positive acceleration, and it's even more now. It's plus 10 in 1 second. It's plus 10 meters per second. When is this point stationary for the first time? I'll give you some choices. A equals 3 seconds. B equals 4.5 seconds. C is equal to 6 seconds. Can you choose for me, please? When is this object stationary for the first time? What do you think? So let's stop this and have a quick look. Mainly A, some B, some C. It is stationary for the first time when its velocity is 0, and its velocity is 0, actually is 4.6 seconds, not 4.5. It's not here because this is a constant positive velocity. The rule that applied over here for a position versus time graph does not apply over here, even though the graphs look the same. So there's a whole bunch of rules you got to work out, and the trick is people will get them confused. One of the skills I might ask you is, what is the average velocity during that time interval? So you draw a line from the start of the time to the end of the time, and you say, what is my rise and what is my run? In this graph, I could say, what is the average acceleration between that time and that time? And for the average acceleration, it's the rise over the run. I could say, what is the distance, what is the displacement in the first 3 seconds? And it's the area under the curve. People have a tough time working out areas under the curve. It's just something that you did it in probably grade school you did it, and you've probably not done it much since then. Breaking this thing up into triangles and rectangles, or triangles and trapezoids, people just are very uncomfortable with. People would get more points from the calculus version than they would from this. And that's not intelligence, that's practice. That keeps coming up. When people stop getting that wrong, I'll stop asking that question. But by and large, most classes, they start off very uncomfortable with the area under a graph. So review that. Make sure, look at the old tests and make sure you can do it. So let's look at this one. I've got to finish in like a few seconds. So what is the average velocity between 1 and 4 seconds? So you put a dot on there. It's a position versus time graph. Average velocity is the slope. You put a dot on there, that's the 1. You find the 4. You draw your line. You go velocity equals my change in position over my change in time, which equals final position minus initial position over final time minus initial time. So my velocity is equal, it's going to be final position is minus 20 minus initial is 0 over final time is 4 minus initial is 1. So V is equal to minus 20 over 3, which equals minus 6.66 meters per second. Make sure you can do that. I'm going to stop that there.